Okay, today we're going to do 3 examples of hypothesis tests, okay? Each one's going to be a little bit different so that you'll be able to see all the different stuff we've learned, okay? So we're going to start with this one, number 57. From generation to generation, the mean age when smokers first start to smoke varies. However, the standard deviation of that age remains constant around 2.1. So they're telling us the standard deviation of the population there. Okay, let's write that down. This is going to be important. So they're telling us sigma. A survey of 40 smokers. Okay, well, let's write that down. They took a sample of size 40. Was done to see if the mean starting age is at least 19. So there's a question that's being asked. The question is mu at least 19? That's the question that they're asking. Okay. The sample mean was 18.1. Okay, let's write that down. X bar is 18.1. With a sample standard deviation of 1.3, okay, S is 1.3. Do the data support the claim at the 5% level? So our level of confidence here, or significance, is 5%. Okay, let's write down our null hypothesis and alternative hypothesis. So the question is mu equal to or greater than 19? So our null hypothesis will be mu is equal to or greater than 19. Our alternative hypothesis, therefore, is mu is less than 19. We will see if we should accept the alternative or reject the alternative. Okay? And this is very easy to do. There is not much to do in this problem. Okay, I want to point out I haven't done anything yet. All I've done is written down the numbers they've given me. Okay? Now I'm going to start doing the work. It's very little work involved here. Okay? Number 1, let me ask you a question. Should I use for this problem the standard normal distribution or a t-distribution? I'm going to tell you the answer. We should use the normal distribution because why? Because we know sigma. If you know sigma, then use the normal. Okay, I'm going to write that down. Use the standard normal distribution since we know sigma. Okay, so very little work involved. All I have to do is imagine the standard normal distribution. Okay, now there is a thing called a two-tailed test, and there's things called one-tailed test. Okay, this is a one-tailed test because our alternative hypothesis is mu less than 19? So we are wondering if mu is smaller than a given value. So that means when I imagine my normal distribution, I'm only going to break off here the tail on the small end. Okay. I'm not being asked if mu is particularly big, so I don't need to look at the tail at the big end. I'm only being asked if mu is particularly small, so I only need to look at the tail at the small end. All right, now they said at the 5% level, so that means that this area here will be 95%, and this area here will be 5%. I look up this number. That's what the book calls the p-value. Okay? So I look that up at the table of normal distribution in the back of the book, or I use Excel. Okay? What? I know it's a z-value, right? I know that, but when you're doing hypothesis tests, the book calls them p-values, even though we're doing a normal distribution. Okay, but nonetheless, what is that value right there that breaks off a tail of size 0.05? Okay, and we look that up. Again, we're not doing any calculations here. We're simply looking up a number in a table, and we get negative 1.645. Okay, now here's the only calculation we have to do. We find the z-score that goes with the sample we were given. Okay, our z-score is, remember the formula, it's x bar minus mu naught, which is 19. That's this number right here, that's mu naught. Okay, so x bar minus that divided by, whoops, wrong color, divided by sigma over the square root of n. Okay, so that's 18.1 minus 19 divided by 2.1 over the square root of 40. That's just a simple calculator problem. And that comes out to be negative 0.602. So where is that located in the distribution? Well, that's located right about here somewhere. Don't worry about is my arrow pointing to the exact perfect spot, because the only question I care about is it landing over here or over here? Okay, so just as long as you draw it on the correct side. All right, so is that in the zone that would favor the alternative hypothesis, or should we keep the null hypothesis? Well, it's not in the tail, so that does not favor the alternative hypothesis. So we reject the alternative hypothesis. So we do not conclude that the average age when smokers start smoking is less than 19. Okay. So there's not a lot of work. I just want to point out again, okay? All of this stuff right here is simply writing down numbers that were given to us in the problem. Okay? This right here is just determining the two hypotheses. This right here is simply looking up a number. And finally, this right here is one calculation. Then you see where that number lands and you make your conclusion. Okay, very easy really when you get the hang of it. Now let's do another problem. An article in the San Jose Mercury News stated that students in the California State University system take 4 years on average to finish their undergrad, 4.5 years on average to finish their undergraduate degrees. Suppose you believe the mean time is longer. Okay, we have a question here. Is mu longer than 4.5? That's our question. Okay. Now, what else do they tell us? You conduct a survey of 49 students. Okay. N is 49. You attain a sample mean of 5.1. Okay, x bar is 5.1. With a sample standard deviation of 1.2. S equals 1.2. Do the data support your claim at the 1% level? Alpha is 1%. Okay, so what is our hypothesis? We are asking, is mu greater than 4.5? So that means our null hypothesis is that mu is not greater than 4.5. Our alternative hypothesis is mu is greater than 4.5. We are being asked if we should accept the alternative hypothesis. Remember this. Sometimes students get a little confused. They ask, how do you know which one's the null hypothesis and which one's the alternative hypothesis? Here's the rule of thumb. When you're doing a hypothesis test, okay, the alternative hypothesis is always the thing that you are being asked, should we accept this? Okay, so you see where it says in the question, you believe the mean time is longer. Does the data support your claim? So we are asking the question, should we accept the claim that mu is bigger than 4.5? Okay, because always the thing that you're asking, should I accept this? That's always your alternative hypothesis. So mu greater than 4.5 is our alternative hypothesis. That means your null hypothesis is mu is less than or equal to 4.5. Okay, now just like before, I'm going to ask a question. Should we use the normal distribution or the t-distribution for this question? Okay, so notice that we do not know sigma, the population standard deviation. We only know the sample standard deviation. So first thing that tells me is I might need to use a t-distribution because I don't know sigma. Okay, If you know sigma, you use the normal distribution. If you don't know sigma, you might need to use the t-distribution. It depends upon how big your sample is. If your sample is smaller than 30 and you don't know sigma, then you use the t-distribution. Okay, now here we don't know sigma, but our sample is not less than 30. So that means we can go ahead and use the normal distribution. Okay. And now you're going to say this. But how are we going to use the normal distribution if we don't know sigma? The answer is we just use S in place of sigma. And why? Because our sample is not smaller than 30. So that allows us to just forget about sigma and use S in its place. Okay, so just like before now. All right, we're only asking the question, is mu greater than 45? So we only need to mark off the tail on the big end. So this is a one-tailed test. Our significance level is 1%. So this area here is 0.99. This area here is 0.01. We look up this p-value here. Okay, and I looked that up for the normal distribution, the standard normal distribution. It's 2.326. We calculate our z-score. The only thing is I'm going to put S instead of sigma because I don't know sigma. That might feel like it's a little bit of a cheat, but remember that that cheat is statistically acceptable as long as n is at least 30. Okay, so let's see here. We have 5.1 minus 4.5 over 1.2 divided by the square root of 49. You just put those numbers into a calculator. Comes out to be 3.5. Okay, where is that located in our distribution? It's over here in this area, isn't it? It's in the tail. That's what's important. It is in the tail. So we do what conclusion? We accept the alternative hypothesis. We conclude at the 1% level that the average time to graduate is greater than 4.5 years. Okay? Again, there's not that much to it. It's just a matter of getting it down how it works. But you're not being asked to do very much. All right, let's do one more. Okay. The mean number of sick days for an employee is believed to be about 10. Members of a personnel department do not believe this. They randomly survey 8 employees. Okay, N is 8. The number of sick days took for the past year are as follows. And then they list them out for us. Okay, so in this one, we actually do have some work to do. They didn't tell us, first of all, they didn't tell us the standard deviation of the population, so we don't know sigma. So we're going to have to use S, the standard deviation of the sample instead. But they didn't tell us that either. So we're going to have to calculate that on our own. Okay, plus the mean as well, by the way. We're going to do the mean first because you need the mean to find the standard deviation. So let me switch that order. All right, so there's a little bit more work here than normal. So let's just spend a few minutes to do those two calculations. This is good review. Okay, so X bar, okay, that's going to be 12 plus 4 plus 15 plus 3 plus 11 plus 8 plus 6 plus 8 divided by 8, and that comes out to be 8.375. Okay, so there's our X bar. Okay, now let's find the standard deviation of the sample. All right, so there's going to be a lot of writing. It's the square root of 12 minus 8.375 squared plus 4 minus 8.375 squared plus 15 minus 8.375 squared plus 3 minus 8.375 squared plus 11 minus 8.375 squared plus 8 minus 8.375 squared plus 6 minus 8.375 squared plus another 8 minus 8.375 squared, and then we divide that all by n minus 1, which is 7. All right, and then you take out your calculator and you calculate that. And I did that, and here's what I got. 4.104. Okay. So they made us do that little bit of extra work, but we did it. Wasn't terribly difficult. All right, now back to the problem. What is the question we are asking? So look at what it says here. The mean, mu, is believed to be 10, but members of a personnel department do not believe this. So the question that we're being asked is mu not 10? That's the question we're asking. So that is our alternative hypothesis. which means our null hypothesis is that mu would be 10. So this is going to be a two-tailed test because to say that something is not 10 means it could be bigger than or smaller than. Whoops. Okay. But what kind of distribution is this that I'm going to look at? Is it normal or t? Think about this. Okay. Do we know sigma? No, we do not know sigma. Is n bigger than or equal to 30? No, it is not. So because we have a small n and we don't know sigma, we must use t distribution. With how many degrees of freedom? 7 degrees of freedom. That's n minus 1. Okay, since we don't know sigma and n is less than 30. Okay, notice also, here's something interesting. They didn't give us a alpha, did they? That means they're leaving it up to us. Okay, so let's just choose alpha to be 0.05. We're just asking about 6 days here. This isn't super important. People aren't going to die if we get the wrong answer. Okay, this isn't a medical experiment or something like that. So therefore, our level of significance doesn't have to be super high, like 98 or 99%. So probably 95% is good enough. Okay. All right, so since we have to do the t distribution, I better put the picture up for that. Okay, there's our t table. All right, let's look up. Before we look something up, let me put the areas in my picture. So we're using an alpha level of 0.05, but it's a two-tailed test, okay, which means that 5% gets broken into two pieces. We got 2.5% here and 2.5% here. 95% in the middle. Okay, now I'm going to look up this number in the t table. Okay, remember our degrees of freedom is 7. It's 1 less than the sample size. Okay, so I go down this column here to the 7. Right there. Okay. This number here is 0.025. So I go across here. Whoops. So I go across here to 0.025, which is right there. All right, now where do those meet? They meet right here. 2.365. That's our p-value, is what the book calls it. Okay, which automatically means, by the way, that this is negative 2.365. Now we calculate our t-score, not a z-score this time, instead a t-score because we're using a t-table, not a z-table. Okay, now that's x bar minus mu divided by s over the square root of n. just like always. Oh, sorry, mu naught. Okay, just like always. So that's going to be 8.375, we calculated for x bar, minus the value we are judging that against, which is 10, divided by our sample standard deviation, which we calculated as 4.104, over the square root of our sample size, which was 8. And we put that into a calculator, and here's what it comes out to be, negative 1.120. So where would that be? That would be somewhere in here. That's our t-score. So is that in the tails? No, it is not. So that means that it is in the range we would expect it to be. If the population mean is 10. Okay, if the population mean is 10, and we took a sample of 8, and we got a sample mean of 8.375, that 8.375 is in the range that we would expect at the 95% level. Another way to say that is this. If instead of doing a hypothesis test, if we instead did a 95% confidence interval centered at 10, then this sample mean would have landed inside that confidence interval. So we reject the alternative hypothesis. And we conclude that mu is not a number other than 10 at the 95% level. Okay? All right, that's it for today. Have a good weekend.